integrals of several variables, it's very often the case that the normal xy coordinate system that we're used to dealing with, the Cartesian system, is not very appropriate for the integrals to be done. This depends on the symmetry of the domain, for example. When we're dealing with functions of one variable, we found it was really important to have the substitution rule to allow us to change variables of integrals. What's the equivalent thing for the integrals of two variables? So in 1D, we have the substitution rule. So if x is a function of u, then I can rewrite the integral of f of x dx as the integral of f of g of u times a derivative of g with respect to u. This is called a change of variables, and effectively it stretches the x-coordinate in a way that makes the integral more easy to do. What's the equivalent of 2 dimensions, and why might we want to do that? We're going to concentrate on one particular example of this, transforming from Cartesian coordinates to polar coordinates. So if we want to describe a point in the plane, we're used to using Cartesian coordinates, but we can equally well describe this point as using two numbers, which are the distance from the origin and the angle theta made with the x-axis. So just as we did for complex numbers, we used a polar form, we can do so for real numbers in the plane using the coordinate transformation. X equals r cos theta, y equals r sin theta. Note there's no exponential form for this, that's a special property of complex numbers. Now if we use these coordinates, lines of constant r become circles as we vary theta, lines of constant theta become radial lines from the origin. And this means that in these coordinates, certain shapes are much easier to describe. For example, the circle is much easier to describe if it's centered at the origin in these coordinates. And in fact, let's just see this. So certain shapes become simple. So a circle of radius a, this goes from being described as the region in x and y coordinates, described in this way in set notation, where points are given by x and y, where x is bound between minus a and y is bound between minus the square root of a squared minus x squared and plus the square root of a squared minus x squared. So quite a complicated thing to describe in Cartesian coordinates, but in polars, this is a set of numbers given by r and theta, where r is between 0 and a, and theta is between 0 and 2 pi. A variety of shapes are much easier to describe in polar equations than in Cartesian. So for example, a circle is just given by the equation r equals a. How do we go from integrating over x and y coordinates to r and theta? It's equivalent to asking what goes in this part here. When we integrate in x and y coordinates, we're picking out small rectangles with an area dA, which is dx dy, and we add up all of those little rectangles to give us the integral that we're after. In polar coordinates, the equivalent of a little rectangle is a little arc of the edge of a circle. So it's a small region like this, and if I call this length dr, and if this is a distance r from the origin, then this length in here is approximately r times d theta, where d theta is this small change in angle. And then the area of this small element is just dr times r d theta. So that implies then, to use polar coordinates to integrate, instead of using dx dy, we use r d theta dr. In general, this transformation is called a Jacobian, and you can read about how to find this in general in the textbook. So let's try an example using this transformation to polar coordinates. So let's find the volume under the function x times y in the region R, where R is given by this region in here, the quarter annulus between 2 and 3. So these are both parts of a circle of radius 2 and 3. In Cartesian coordinates, this is an extremely complicated problem. But in polar coordinates, the region R is given by what is effectively a rectangular region in R and theta, because R is bound by the constant numbers 2 and 3, and theta is bound between the constants 0 and pi by 2. If I transform this region to R and theta, we have a rectangular region. The area of xy dx dy then becomes something that I can evaluate, which is x times y is r cos theta times r sin theta. The integral element dA becomes r dr d theta, and the limits, if we do the r integral first, is from 2 to 3, and the theta integral is 0 to pi by 2. Let's swap these integrals around, which I can do because the limits are constants. Then we can do the theta integral, which becomes sine squared theta over 2 between 0 and pi by 2. This gives me a half the integral from 2 to 3 of r cubed dr, which all simplifies to 65 over 8. Let's now see an example of this type of transformation, which can be used to evaluate a one-dimensional integral which would otherwise be impossible. Let's try and find the integral of e to the minus a half x squared, which is called a Gaussian function. Let's integrate that over the entire real line from minus infinity to infinity. How do we go about doing that? In fact, why am I even bringing up such a problem in the context of multivariable calculus? Well, there's a trick to doing this, and what we do is we realize that we can also write the same integral in terms of y. Because y is integrated over an infinite range, whatever symbol I use in there doesn't really matter. And so now I can form the value I squared as a product of these two integrals. And because one integral involves just x and the other one just y, I can combine them both into a double integral. And simplifying the exponential is the reason for doing it. Because this exponential now depends on x squared plus y squared, if I transform to polar coordinates, that will just become r squared, making the whole integral a completely different type of integral to do. The reason it's completely different is because when I transform from dx dy, that part transforms to r dr d theta. And we'll see why that makes a big difference just now. So in polar coordinates, this now becomes, still have a double integral, we'll figure out the limits in a second. X squared plus y squared equals r squared, and the dx dy becomes r dr d theta. So the theta is the outside integral. It involves the entire two-dimensional plane, so that means that r goes from 0 to infinity, and theta goes from 0 to 2 pi. The integrand doesn't depend on theta, so that's easy to evaluate. That just gives us a 2 pi factor. Now we see why we've done this strange transformation. The integral r times e to the minus a half r squared is easy to do by substitution. So with this substitution, the integral now becomes just the integral of e to the minus u du, and the limits are still 0 to infinity. And this now becomes a very straightforward integral to do. This just comes out to be 2 pi. And therefore the integral that we started with is just the square root of 2 pi. So that's a very neat trick for doing an otherwise impossible integral.